called so broadly speaking, imitation learning, this is referring to this problem of kind of using demonstrations from an expert to learn a policy for sequential decision making. Let me try to close out of this thing up here. Sorry. Sorry. Oh, okay, there's the cursor. Great. Sorry about that. Okay. Yeah, so imitation learning, just to get back into this, this is this problem of, yeah, using demonstrations from an expert to learn a sequential decision-making policy. So just to go through an example of this, let's say we want to learn, you know, like train an AI agent that can drive a car. The way we do this is we first gather a bunch of demonstrations in which an expert drives the car. So things like, what were the sensor inputs to the car and what action did the expert take? Once we have these demonstrations, we'll use like a machine learning to fit a model that tries to predict the expert's behavior, right? So like, what was the expert's action given, let's say the sensor inputs like camera images or this sort of thing. And then once we have this, we get a model that we can treat as a kind of policy that then we can go and deploy and use to make decisions on its own in the future. So this is not a new paradigm, imitation learning. But I would say it's become increasingly widely used over the last decade, especially in the context of like robotics and embodied decision making. Also in the context of language modeling, and I'll try to spell that connection out a little bit more in a second. One way to think about it is that it's a simpler kind of alternative to different techniques like, say, reinforcement learning. So with reinforcement learning, kind of the only supervision you get is a reward signal that tells you how well you're doing. So you kind of need to explore your environment and learn which actions are good and bad through trial and error. With imitation learning, you have this very strong supervision just from the expert directly. And this kind of removes the need to like explicitly explore the environment or do trial and error. So like rather than needing to use these RL tools, you can often get away with using more like supervised learning tools, which are typically, more sample efficient and more stable. And so kind of given this interest in applying imitation learning more and more broadly, what I wanted to do in this talk is try to revisit just the basic theoretical foundations of imitation learning and try to understand, are the algorithms we have right now the best we could hope for, or can we try to make them, even more sample efficient and more stable? And I also kind of want to look at to what extent does the existing theory capture the state of affairs in practice. So for this talk, we're going to focus on two different frameworks for imitation learning. The first is called offline imitation learning. This just means we have to learn from logged demonstrations or trajectories from the expert. And the second is online or interactive imitation learning. This is where we can actually interactively query the expert at training time. So let me give a quick primer on these and try to explain like why would you use one or the other one? What do the basic guarantees look like? So we'll start with the offline imitation learning. We're going to formalize this by working in what's called an episodic finite horizon Markov decision process M. So we have a horizon H, X is the state space, A is the action space, P is the sort of transition distribution, and R is the reward function. And the way that an episode will work in this MDP is we fix some policy pi. This is just a mapping from states to actions or distributions over actions. And at each step, little h in the episode, we look at the current state xh. We sample an action AH to play from the policy. Based on the state in action, we see this reward RH. And we transition to the next state by sampling from the transition distribution. Okay, so that's the MDP setup. In offline imitation learning, our goal is to kind of find a policy pi that has high reward in this MDP M. We don't get to directly interact with the MDP. Rather, what we get is a data set, which I'll call script D, which consists of n trajectories or experts, which are demonstrated by running this expert policy pi star. So each of these trajectories is just this sequence of state action, state action, state action that we get by, starting at x1, sampling the action from pi star, proceeding to x2, and so on. Okay, so we have these trajectories. Based on these trajectories, what we would like to do is learn a policy pi hat such that the reward of pi hat is almost as good as the reward of the expert policy. So j pi here denotes the expected reward when we run a policy pi in the MDP. So we just want j pi star minus j pi hat to be small. This just means pi hat's almost as good as pi star.
Is the agent given R?
Great question. The agent is not given R in this setting. So we only have the yeah, exactly. Yeah, this is a really important thing to emphasize. So in this protocol, we do not know R, and we also cannot directly interact with the MDP. So all that we have to learn the policy is just these data sets of, state, expert action, kind of all that we can do is try to imitate the expert's actions. How do we do this? Probably the most well-known and widely used technique is what people call behavior cloning. This goes back to the work of Pomerleau on self-driving in the 80s. And the idea here is just to try to solve this using kind of standard supervised learning, to kind of reduce to supervised learning. So let's imagine, to keep things as simple as possible here, that the expert policy is deterministic. Then what we're going to do is just minimize this kind of classification loss, where the classification problem we're trying to solve is just, for each example in our data set and for each state, try to predict the expert's action as a function of the state. We're using indicator loss here for simplicity. Obviously, you can imagine using, your favorite machine learning loss, like square loss, log loss, etc. And that's it. That is very, very simple algorithm. I would say that that's, one of the main appeals of this algorithm is that it's very simple and it's very flexible. You can kind of just take your favorite model or algorithm for supervised learning and, just let it do its thing on this data set, right? So, when I write argmin over pi and pi here, really what we imagine is pi is parameterized by a neural net or something like this, and we're running gradient descent or something. But one potential issue with this sort of algorithm is it is seemingly ignoring the sequential aspect of this decision-making problem. And this is something that can lead to an issue that is often described as distribution shift or error amplification. So the idea here is, we're minimizing this training loss, but if the pi hat that we learn has errors, it's not perfectly matching pi star, then the distribution over states that we encounter at test time, when we run the policy, can be different from the distribution over states that appeared in our training data set. They're the same at step one, but perhaps pi hat makes a small error at step one. We go a little bit off course. Now perhaps I make another error. We drift a little bit further off course. And before long, we end up in some portion of the state space where we don't have any examples, or we didn't have any examples at training time, and maybe we don't know what to do. That's a concern, at least. In theory, the way this is traditionally manifested is through the role of horizon on the sample complexity of imitation learning. So sample complexity here just means, how many demonstrations or trajectories do I need to learn a good policy? So there's kind of classic results here that suggest, okay, if your rewards are bounded by 0, or let's say are in the range 0 and 1, then you need something like h squared or horizon squared trajectories in order to learn a good policy, say a policy that has 10% error. So one of the h factors here is just coming from the fact that there's h steps. This would be there even if our states were IID and we had no control over them. The other h factor is coming from this sort of distribution shift phenomenon. And so this is suggesting that there's perhaps some fundamental hardness of this problem that is not there if you were doing pure supervised learning. And we'll come back to this and really get into the details of it in just a second. But this instability and this sort of quadratic sample complexity, this is what's motivated the other paradigm I mentioned before, which is online imitation learning. So for online imitation learning, we don't get to, we still do not observe the rewards. But now we are actually able to interact with the MDP and the expert sort of during training time. So the protocol for this setting is I'm given n episodes. At each episode, I can pick whatever policy I want and deploy it. This gives me some trajectory. And then the trajectory is annotated with the expert's actions at each state. So like for each state that I encounter, the expert tells me like what they would have done instead. So this is a stronger access model. You know, it requires sort of having the expert around while you're training the policy, but this can give better sample complexity. So there are these algorithms, probably the most famous one is called Dagger. There's another very well-known one called Aggravate. These come from this influential PhD work of Stefan Ross. And the idea behind these algorithms is you kind of learn a policy, you roll in with it, you know, you use the expert's feedback to correct yourself, and you kind of keep doing this iteratively. And what these allow you to do is they allow you to achieve sample complexity that's linear in the horizon H, at least if you have an MDP that's nice in the sense that you can recover from taking bad actions. And again, I'll explain what this actually means formally in just a second. Okay, but this is a nice result. The only drawback is, of course, you know, this online interaction is not always realistic. Like if you were imagining, you know, training like a robot arm or something, this kind of means you have like an operator sitting around 24/7 operating the robot arm while your algorithm is running. And so this will motivate the main question I want to look at in this talk, which is to understand to what extent is online imitation learning, you know, truly more sample efficient than offline learning? Like, is this H versus H squared fundamental, or can we perhaps improve existing algorithms and analyses? And yeah, we're going to focus on the role of horizon here, just because this is kind of classically been the focal point of theoretical results on imitation learning. I'll just briefly say a little bit more about why I got interested in this problem before getting into the details. One reason that this piqued my interest is actually a connection to like autoregressive language modeling. So, you know, you can do behavior cloning with many different supervised learning losses. If you use this log loss or cross entropy loss, then this is actually identical to this well-known like next token prediction objective for language model training, which is kind of, you know, like the substrate on which all of language modeling is built. Like formally, this is a special case of this setting where you interpret the language model as a policy in this token level MDP, where your action is like, what is the next token I want to predict? And your state is just all of the tokens that have been predicted so far, as well as like perhaps a prompt. So one motivation for just looking at these basic kind of statistical questions around imitation learning is just as a lens to try to understand, you know, just basic statistical and algorithmic questions around language modeling. Like, is there opportunity for improvement here? One thing I found interesting is this phenomena of like distribution shift and error amplification. This is something that has been discovered sort of multiple times independently in both lines of research, so imitation learning and language modeling. This to me at least suggests that there's some real common ground. A second motivation is just, if you think about the current paradigm for language modeling, there's kind of two phases, right? One is like pre-training, which, you know, you can view as just training this large foundation model through imitation learning. And then the second stage is, you know, you usually fine tune to a task of interest, typically using, you know, reinforcement learning, or what's called RLHF. I think if you draw inspiration from this, it's easy to imagine a future where you kind of apply that paradigm to, you know, all of interactive decision making beyond just, you know, language modeling. So, you know, say things like embodied decision making, self-driving, robotics. You know, perhaps you know, first train a foundation model, say a foundation model for embodied decision making through imitation learning, then you fine tune with RL. And so, you know, understanding just the basic kind of algorithmic and statistical foundations around imitation learning, you know, it seems useful here both for doing this first phase where you train the foundation model, but also for perhaps guiding how we best design algorithms for this second kind of fine-tuning phase. Okay, so with that out of the way, sort of the plan for this talk, what I want to do is as follows. I want to come back to behavior cloning and like dive into the details of why does this have poor horizon dependence. The main result will be to show that by tweaking this algorithm slightly, we can actually improve the sample complexity and kind of close this gap between online and offline. And then the last part will be to kind of think about, in light of these results, if not through horizon, then where can online imitation learning, really lead to benefits, and where's the biggest opportunity here to kind of align theory and practice? Okay, so that's the plan. Let's come back to the behavior cloning. Okay, so I'm just displaying the same behavior cloning algorithm I was showing before. I just want to sketch where the dependence on horizon is coming from in this classical analysis. We'll start by making some basic statistical assumptions. We're going to focus on the case where pi star is deterministic to start. We will handle the stochastic case later, but the sort of intuition will be similar in both cases. The next assumption we're going to make is, this will be called a realizability assumption. So what this says is, when I do this algorithm up here, I'm minimizing over this class pi. This is kind of just, this is capturing how I'm parameterizing my policy, right? This could be a linear model, it could be a neural net. What kind of policy class will depend on the, perhaps the domain, but we're just assuming that this policy class is flexible enough to actually capture the experts. So this is perhaps the most basic setting you could study. Okay, and the last assumption we'll make will be probably the most important one to keep in mind throughout the talk. So we're going to make a normalization assumption on the rewards. What we're going to assume is that the cumulative reward, like the total reward I can get in each episode, is normalized so that it lies in the range 0 through r for some parameter r, which we will leave as a free parameter throughout the talk. If you're in a setting where maybe you get a single reward of 1 if you reach a goal and that's it, then this r will be like 1 or constant. If I'm in a dense reward setting where I can get a reward 1 at every step, then this can be as large as the horizon. We're leaving this as a free parameter just to distinguish between, where are we getting dependence on horizon that comes purely for scaling reasons versus dependence on horizon coming from, more intrinsic reasons, right? And yeah, I would say most of imitation learning theory is focused on this dense reward case. Okay, let's start by going through this analysis. I'll start by just defining a quantity I'll call like LBC here. This is just sort of like the population version of the behavior cloning loss that our algorithm is minimizing, right? This is just average overall steps H. What's the probability that our policy disagrees with pi star if we draw the state by executing pi star? Okay, so the first step here is, because we're minimizing the empirical version of this behavior cloning loss, and because pi star is in our class, if we just do a very standard like concentration or like uniform convergence argument, this will tell us that the behavior cloning policy has this population level behavior cloning loss bounded by roughly like log pi over n. If we have a finite class of policies pi, this is just a classic sort of supervised learning style generalization guarantee. I'm working with a finite class here just to keep this, as simple as possible, but morally this is just a proxy for like the generalization error, and you can replace this by, any other standard sort of like learning theoretic complexity measure like VC dimension or Rademacher complexity or anything like this, just using like completely standard arguments. But so morally, whenever you see log pi in this talk, you should just think of, generalization error or uniform convergence. Okay, so that's step one. For the second step, you can show that for any pair of policies pi star and pi hat, the difference in reward is bounded by RH times this behavior cloning loss. This comes from this kind of what's called the performance difference lemma, which is this telescoping argument. Morally, what's happening here is, you're getting a factor of R just from the range of the rewards. Like this is what you can pay if you make a mistake. And this H factor is coming from kind of a distribution mismatch where what I care about is what's the probability that I make an error under the state distribution induced by pi hat, but what I'm minimizing is the distribution under pi star. Okay, and if you combine these, you get that your suboptimality is bounded by RH times log pi over n. So this means if we're in the dense reward setting where we have R equals H, you know, we need something like H squared episodes to make the right-hand side here constant. And so this is what people mean when we say like behavior cloning has quadratic sample complexity, right? Really, it's just RH, and RH just is H in this sort of standard dense reward setting. Okay, so maybe these are loose. Maybe these steps of the analysis are loose. Let's come back. The first step here is actually tight, even if you only have 2 policies in your class. This is kind of coming from the dependent nature of, you know, the data that you're using, right? These are like trajectories, and things are not IID within trajectories. You know, you might imagine, you know, your data set kind of has n times h examples for this classification problem because you have n trajectories, h state action pairs in each trajectory. But yeah, things are not IID, and so you're only getting a 1 over n rate rather than something like a 1 over nh rate. In step 2, I won't go into details, but you can show that this is tight, even if your MDP only has 3 states, kind of precisely because of this distribution shift issue. And so this is a little bit disappointing. This is what will perhaps bring us back to looking at the other algorithms I was mentioning, these online imitation learning algorithms. So formally, these online imitation learning algorithms give improvement over the bound I just showed. Yeah.
When you say it's tight, do you mean it's a low bound for all algorithm or just for the YARA?
Great question. I mean tight for this specific algorithm.
Okay,
Yes,
okay,
yes.
okay.
Right. The question of whether it's tight for all algorithms is precisely, you know, that's kind of like what we'll try to actually answer in this talk. Yeah. But yeah, just to come back to online imitation learning, this gives about an improvement over what we just showed. When this you have bounded what we'll call recoverability. So to define this, we're letting q pi star here. This is kind of the value function or q function for pi star. This is just saying if I start in state X and take action A and then run pi star until the end, what reward do I get? So what recoverability is looking at is essentially it's looking at if I start in state X and I take an action other than the expert's action, but then switch back to the expert, what is the worst that I pay for doing this? So this is kind of asking, like, how hard is it for me to correct back if I make a wrong action, but then correct myself afterwards? You know, if your states are IID, this will just be like 1. But in general, it can be as large as R. But yeah, it's a problem-dependent parameter. It can kind of interpolate between these regimes. And what these online imitation learning algorithms get is something like mu h log pi over n. So you're replacing R by mu. And so this is giving an improvement. This is getting you down to linear dependence on h whenever this recoverability parameter is constant. You know, this is suggesting that perhaps Dagger and these online imitation learning algorithms give some, like, you know, some real improvement over the offline setting. The result I'm going to show now is that the situation is actually a little bit more subtle. We can actually, at least in this realizable setting, improve the sample complexity of behavior cloning to be completely independent of the horizon. So even if we only have fully offline or like logged data, we can, you know, not just match, but actually do better than the bound I just showed. The only catch here is the loss function is important, and it will be, to get this guarantee, we'll need to kind of switch back to using this log loss or cross entropy loss function. Okay, so let me dive into this result. So yeah, our starting point is we're going to look at this variant of behavior cloning where we're replacing the indicator loss with this kind of log loss or cross entropy loss. So this is a loss function that you know, beyond just having statistical benefits is actually just useful because it is well suited to stochastic policies in addition to just deterministic policies. So going forward, we're going to write this for general stochastic policies. So pi of a given x is, the probability that pi selects a given x. So all we're doing here is we're averaging over all the trajectories, averaging over all the steps h, looking at the log 1 over the probability that pi selects the expert's action. And that's it. Like, that's the only change. Why is this beneficial? It's instructive to look at the case where both pi star and pi are deterministic. This is a very extreme case, but what you'll see in this case, right, is that the log loss, unless pi agrees with the action selected by the expert for every single step h in our data set, this is just infinity, right? Because if pi is deterministic and it selects the wrong action, you're just dividing by 0 here. So one way to think about this, this is a little informal, but we'll come back to a formal version, is you can think of this as kind of like a more stringent indicator loss, where you're giving a penalty if you deviate at any point along the trajectory rather than on average across the trajectory. And this is what I will show can kind of lead us to get fully horizon independent guarantees once we normalize for the range of rewards. To do this, the first step, sort of similar to what we just did in the analysis of indicator loss behavior cloning, is we want to prove like a supervised learning generalization guarantee for this loss function. One thing that's kind of subtle about the log loss, but is actually very closely related to the intuition I was just sketching, is it's subtle to prove generalization bounds because it can be unbounded, right? Like, standard kind of concentration inequalities, like say Hufting, which require bounded random variables, these don't immediately apply. But we can use this kind of more information theoretic machinery developed in statistics to analyze this. This is going to tell us that even though we're minimizing the log loss, without any assumption on boundedness or anything, we'll get a guarantee with respect to this other divergence called Hellinger distance. Hellinger distance, this is just defined for two distributions P and Q, is like the sum of the squared errors between the root probabilities. Morally, this is kind of like a smoothed out version of KL. So if you're like on the interior of the simplex, it behaves almost the same as KL, like they're equivalent up to multiplicative constants. But on the boundary, it doesn't blow up, like it stays bounded. Okay, so we're going to get a generalization guarantee with this thing. The way this will work is we're going to define this quantity I'll call P pi here. So this is just the law of the trajectory when we run the policy pi, law of the full trajectory. When we do behavior cloning with the logarithmic loss, you can actually interpret this as maximum likelihood over the set of P pi's induced by your policy class. The idea is just if you write out the log probability of the trajectory under this law P pi, this factorizes into the probabilities of the actions selected by your policy pi and the transition probabilities in the NDP. Okay, but the transition probabilities do not depend on the policy you're optimizing over. So, like the minimizer for this loss function and this loss function will be the same. And so if we use a standard kind of generalization guarantee for MLE with Hellinger distance, what this will tell us is as long as pi star is in our class pi, then with probability at least 1 minus delta, the Hellinger distance between the law of trajectories induced by pi hat and induced by pi star will be bounded by log pi over n. So this is the same guarantee that we got for indicator loss behavior cloning, but it's with a stronger kind of notion of distance between the policies that we're learning. And just to note here, this holds for any pi star, regardless of whether it's deterministic or stochastic, as long as it's in our class pi. So this will be our kind of new notion of generalization error going forward. Okay, so now that we have this, I can kind of state our main result. I'm going to start by stating it in the case where pi star is deterministic, and then we'll move to the more general case where pi star is stochastic. The stochastic case is just a little bit simpler to state, so the deterministic is useful as a warm-up. Okay, so the first part of this guarantee is just kind of a general reduction style result that relates the sort of suboptimality of the policies to the Hellinger distance. So what this says is for any expert policy, deterministic expert policy pi star and any imitator policy pi hat, the suboptimality is bounded by the reward range times this Hellinger supervised learning error. If we plug in the generalization bound we got on the previous slide, then what it tells us is for any expert policy, deterministic expert policy pi star, the suboptimalities at most are times log pi over n. So to compare this to what we had before, if we compare against this bound for vanilla behavior cloning, we're going from RH to just R, so we've shaved off the H factor. This is also tighter than this mu H bound we got for dagger, unless you're kind of in this like very trivial regime where the mu is like 1 over H. And more broadly, this is just I guess the tightest sample complexity guarantee for offline imitation learning that I'm aware of, at least. Let me go through an example of this and just kind of to try to emphasize that there are not really like hidden H factors here in the R or the log pi. So as an example, I think it's instructive to look at this case of stationary policies, or more generally just policies that have kind of parameter sharing across the steps H. So just to give an example, if we looked at linearly parameterized policies where phi is some feature map and theta is some parameter, parameter sharing just means the parameter theta we're using here is the same regardless of what the step H is. So when you have parameter sharing, generally speaking, this log pi, this supervised learning error, is going to, this will depend on like, problem dependent parameters that reflect, just how rich is your function class, but it generally will not scale with the horizon. So for example, if you look at the simplest case where you have a finite state and action space, then pi is just a set of all policies over this space, log pi will scale with the number of states, it will not scale with the horizon. If we look at this linear case, log pi will scale with the feature dimension, but again, it won't scale with the horizon. And so if we come back to this bound, this tells us, if we're in this regime where R is like order 1, so sparse rewards, then truly we do not need the number of trajectories we need to learn an epsilon optimal policy, does not depend on horizon, right? Like this only depends on whatever problem dependent parameters are popping up here. If we're in the dense reward setting, okay, we will need H over epsilon trajectories just because of the R is H, but we're still beating this quadratic cursive horizon that I was showing earlier. Yeah, question.
So I'm trying to now compare your previous discussion.
Yeah.
I think you derived the H, but you told us that it would be associated with the distribution shift.
Yeah.
Say a little more about where the H came from. So.
Yeah. Well, you mean for the indicator loss behavior cloning? Yeah. In like classical analysis for the indicator loss behavior cloning, this just comes from some inductive argument where, like, maybe just to write it out here, you have some bound on like p pi star that like pi xh is not equal to pi star xh. And the way these classical analyses proceed is what they actually want to be bounded is p pi hat at pi of xh is not equal to pi star of xh. And where you get an h is just by kind of trying to inductively bound this quantity in terms of this quantity. Like I can bound the probability, like say I'm looking at a particular step little h. If I know that pi agrees with pi star for all of the steps 1 through h minus 1, then the state distributions these induce at step h will all be the same. And so you kind of pick up an h by, inductively bounding these probabilities kind of one by one. That's the idea.
Is this H kind of?
Yeah, it can be, yeah. Yeah. Well, okay. Certainly like the instability that people ascribe to this empirically is there. to what extent is it actually coming from this phenomenon? That's a subtle point, and that's one I actually want to come back to at the end of the talk. Yeah. Okay, let me make two remarks on this. Oh. Sorry, having some clicker trouble here. Let me come back. Yeah, maybe. Oh, sorry. Okay, hopefully everyone can see that again. Yeah, just a quick remark on this is that the fact that we have squared Hellinger distance in this bound is important to get this result. So something like this trivially holds for TV distance. Just this is basically the definition of TV distance, as well as for like Hellinger without the square. But this will give you a kind of like slow rate because you'll get 1 over root n, and so this will not give you this property where you're beating the h squared cursive horizon. Let me come to the stochastic case. So for stochastic policies, the main result here has a similar flavor to the deterministic case, but it's going to scale with a notion of kind of variance for the optimal, or not for the optimal policy, but for the expert policy. So there's q pi star here again is this state action value function. V pi star is the state value function. This is just the expected value if we start in state x and run pi star. And this variance, what this is looking at is it's summing over all the layers h and then looking at the expected deviation between v pi star and q pi star. So this is somehow capturing like what is the variation in the expert's own reward if you run them. This is 0 if the expert is deterministic. And so what the stochastic result says is this has 2 terms. The second term in this bound is the same as what we had in the deterministic case up to log factors. It's r times squared Hellinger. The first term is root of the variance times the squared Hellinger. So if you plug in, again, the supervised learning bound for Hellinger that we were showing before, we get r log pi over n for the second term. We're getting an extra log factor here. And then for the first term, we have root variance log pi over n. So just to spell out kind of how this behaves, this is scaling as 1 over root n. So this is a slower rate than the deterministic case, but we're recovering the deterministic case when the variance is 0. And this actually is like fundamental, like no algorithm can do better than 1 over root n if the expert is noisy. This is also still horizon independent. So this is not obvious a priori because this sigma pi star, it's the sum of h things. This looks like it should scale with h. But there's kind of a law of total variance type going on where you cannot have all of these terms in the sum be big simultaneously. So this is actually always still bounded by r squared. So this tells you to learn an epsilon optimal policy. In the worst case, something like r squared over epsilon squared trajectories suffice. This is worse than the deterministic case. You're getting r squared instead of r. This also turns out to be fundamental. So you need to have the r squared in this setting. Let me say a little bit about how you prove these. I'll start with the sketch of how we prove this sort of main theorem in the deterministic case. This is kind of formalizing this idea that I was trying to sketch earlier, that using the log laws kind of gives you control over like trajectory level deviations between pi hat and pi star. So kind of the main thing we're going to use to do this analysis is this trajectory level distance function. So what this is asking is, say I start with policies pi and pi prime. I sample an entire trajectory from pi. Then for each state I encounter, I resample another action from pi prime. So this is like a tangent or like ghost action. And then I look at whether any of them disagreed. So for the first step of this analysis, we can show that for any pair of policies, the regret is bounded by just r times this trajectory level distance. This is pretty simple. Just like if the policies agree everywhere, you're good. If not, you can just write it off as r. The second step here is a little more technical, but what this says is if pi star is deterministic, then the Hellinger distance we were looking at is lower bounded by this quantity. And then the last step is that this trajectory level distance is actually symmetric, even though it might not look like it a priori. This is kind of an inductive argument. And it's actually similar to what I was just trying to show on the board, right? Like if pi and pi prime never deviate from each other up to a certain time step, then they're actually inducing like the same state distribution. So you can use that to argue that you swap the role of these in this definition and you get the same value. And so if you put all three steps here together, you get this bound. I also want to sketch the stochastic case. This one is a little bit more technical and more interesting. I haven't been doing this in talks on this work, but I wanted to throw this in here just because it is math. We're doing math after all, So let's have a look at this one. So just to recap, this is the stochastic result, right? This is I want to bound my regret by root variance times Hellinger plus R times Hellinger squared. So to prove this, we're going to use a little bit more of an information theoretic argument. Our starting point will be this change of measure lemma. So just to motivate this, you might be familiar with this basic result that, if I have a function bounded in, say, 0 through R, I can bound the difference in expected values under a pair of distributions P and Q just by the range times the TV distance. But that requires a bound on the range. So what this is saying is you can bound the difference in means of a function f under P and Q by the root of the Hellinger distance times the sum of the second moments for f under P and Q. So this is a kind of sharper change of measure argument in the sense that it only requires a bound on the second moment. It does not require the function to be bounded. But one consequence of this result, which is nice, is if you have a function that is bounded, you can get something like expected value under P is bounded by 2 times the expected value under Q plus the range times the squared Hellinger distance. So this is, again, is an inequality where it's like you get rid of the 2. It's very obvious that this holds if you replace this with Hellinger distance. But here you're kind of getting a faster rate with squared Hellinger distance at the cost of this multiplicative factor. But that'll be fine for our purpose. Okay, so how do we do this? So we're going to define this quantity I'll call delta of tau here. This is just the sum of differences between b pi star and q pi star for a trajectory tau. But by a simple telescoping argument, we can write the regret between pi star and pi hat as the expected value of this delta quantity under pi hat. And what you'll also notice is the expected value of this delta under pi star is 0, right? Because this again is sort of capturing on average to what extent is pi hat deviating from pi star, right? So we're going to apply this change of measure argument to delta. So this tells us that the expected value under pi hat is bounded by the expected value under pi star, which is 0 plus root of the second moments for delta under pi star and pi hat times this Hellinger distance. Okay, so what do we do with these second moments? Well, the second moment under pi star, this is exactly equal to the variance that we were looking at. This is just because under the law of pi star, this is like a martingale, right? Like each of these increments here is like conditionally mean 0 when you condition on xh. So if you expand the square here, all the cross terms cancel. The problem in proving this is what happens under pi hat. So here's a simple way to handle this. If we use this second lemma here, this sort of multiplicative change of measure, we can bound the second moment under pi hat by 2 times the second moment under pi star. But we're going to pay for the range of delta. And this delta can be as big as r times h, because each of these increments lies in the range r, and there's h of them. So we get rh squared here. If we plug these into the previous bound, we get the right term for this part, but we have this spurious h factor here. So this is not recovering the right thing in the deterministic case. Okay, so how do we deal with this? Well, we can do some concentration. So what it turns out, right, is, so, okay, we want to tighten this inequality. We'd like to get rid of this h here. It turns out that like, so this delta, again, this is the sum of these like v pi stars minus q pi stars. This can be as large as rh in the worst case, but it actually does concentrate well. So like with high probability, this thing is bounded by just r. So something like r log 1 over delta. This is not like a standard consequence of like, say, Hufting or like these Friedman inequalities. This is, you kind of have to look at the specific structure of the problem and use the fact that the variance of this thing is like very well behaved. So the variance, this is kind of saying that you have like a law of total variance in probability. So with this, you're almost done. So this is like almost enough to just replace this RH squared here with just R. The only issue is this is only saying that this is bounded with high probability under pi star, and we also need to worry about pi hat. So the way you kind of wrap this up is we truncate this delta. So we like stop it whenever it exceeds roughly R. And we could do some more kind of like martingale arguments to argue that the, you know, the error incurred by truncating this thing or stopping it is not that big if this Hellinger distance is small. So, but morally, that's the idea, is like this thing is usually bounded by R, and that's enough to kind of tighten this argument. One interesting thing that remains is like the reason why we have log factors in the final bound is just from like this part. So that would be, I'm curious if that could be removed. Okay, let's see. How are we doing on time? I guess I've got about like 10 minutes left. Okay. There are two things I wanted to briefly discuss. One is to what extent does this like bear out empirically? The other is to come back and look at what are the implications here for like the gap between online versus offline imitation learning. I think I may skip the experiments here just in the interest of time. I guess what I'll briefly say is what we kind of tested is if we look at these standard like benchmarks that people use for reinforcement learning, so things like the Mujoko, which is this continuous control task, or like control in Atari, you know, to what extent do you actually see this horizon independence phenomenon if you like put yourself at least in the setting where all the theoretical assumptions hold? So you have this realizability, reward rate is are normalized, so they're in the range 0 through 1. And what we found was that like this, you do actually see this horizon independence in this regime. So both for yeah, continuous control and also Atari, if you look at, you know, if you do some experiment where you train an imitator for multiple choices of horizon and multiple choices of the number of trajectories, what the x-axis here is showing is, you know, learning curves as a function of number of trajectories, y-axis is regret. The lines are just different choices for the horizon in your learning problem. For the continuous control, okay, things are not getting worse with horizon. For Atari, you're actually doing better with horizon. This is kind of interesting because you know the theory says we should not be doing worse with horizon. You definitely can do better in principle if you're in a setting where you have, let's say, like very weak correlation across the steps H. Or perhaps you have very strong correlation in a way that allows you to like reuse things you learned at step 1 at like larger time steps. So it would be interesting to do, I guess, more theory and kind of look more deeply at, you know, when can this actually happen? Yeah. But I'll defer to the paper for more details on these. I'll just mention also we did similar experiments with some simple like language modeling tasks and found similar conclusions. But yeah, I don't really have time for that. Okay, let me just come back to this last point, which is what are the implications here for the gap between online and offline imitation learning? Like where do we actually expect online interaction to bring benefits? So what we have here, this is a lower bound, like an information theoretic lower bound. And this suggests that the improvement we're getting, like the fact that this bound that we're getting in the offline imitation learning setting is as good as, you know, what was previously known for the online imitation learning setting. This is suggesting this is fundamental. So what this says is, for at least for a worst case policy class, yeah, there exists a policy class where, you know, all the assumptions we're making hold. So you have bounded rewards, you have realizability, the expert is deterministic, and this recoverability constant is bounded, where for a worst case choice of an expert policy in this class, no algorithm can do better than h log pi over n, where h here is, this is just for the case where r is h. So this is the same as the r log pi we had in the previous bounds. Yeah, so this is saying for at least a worst case policy class, no algorithm either online or offline can, you know, do something tighter than the bound we're getting with log loss behavior cloning. Yeah, even if all these nice properties hold, like even if the dynamics are actually known as well as stationary, even if the rewards are stationary, even if the expert policy is stationary. So like this is saying that there's a sense in which like at least for a generic pi, this gap between online and offline imitation learning is not fundamental. The caveat here is this is a worst case result. This is for like an adversarially chosen policy class. And there are specific policy classes where online imitation learning can like provably do better than what any offline imitation learning algorithm can achieve. In particular, what this paper shows is if you're in the setting where your policies are like fully non-stationary, like there is no parameter sharing between any of the steps H, so you're learning a totally different policy at each step H, then online imitation learning can do better than offline imitation learning. And that's fundamental. I guess my take on this is, I think there are many ways in which online imitation learning can be beneficial over offline, but I think we do probably need to go beyond just looking at horizon to really capture these. And perhaps look at things in a more like problem dependent and like less worst case sense. I'll just mention a couple considerations that are not captured by the theory I was presenting today are, yeah, misspecification, like what happens if your class pi is not strong enough to represent pi star. Also like instability, like here for this, we're assuming everything is bounded like almost surely. We're also kind of tacitly assuming that things are discrete by saying that we can like minimize the log loss and drive this error to zero. So I think, yeah, going beyond that, looking at these is perhaps interesting. The misspecification I've been thinking about a bunch actually, and I would say it's still actually not that obvious that the online is super helpful here. These are perhaps more classical ones. There are also interesting examples where the online imitation learning can be helpful that I don't really think have been explored before, and we have some of these in our paper. I'll just give like a teaser here. One reason it can be helpful is representational benefits. So like the idea here is for offline imitation learning, you're kind of just directly trying to learn the behavior of pi star. If pi star is like randomized and good actions are not necessarily unique, then what these online imitation learning algorithms do, which is like start with a rough guess for pi hat and then try to like correct it, this can be a simpler learning problem than directly trying to model pi star. In the sense that like, you can get away with using a smaller or less expressive policy class and solve the problem. And so we have some example in the paper where you can get like an arbitrarily large separation, like information theoretically between online and offline because of this phenomenon. But that's a very stylized example. Like understanding this more generally would be interesting. Another one I'm quite interested in right now is exploration. And like the idea with this one is, if you have online access to the MDP, then rather than trying to do these sort of like, I would say fairly simple schemes where you just like learn a pi hat, correct it, try again, correct it. You can try to do much more deliberate schemes. Like you can try to like visit states that you think will be as informative as possible for trying to distinguish pi star from other candidates. So this is another thing that, yeah, you can come up with stylized settings where this does give like an arbitrarily large separation between online and offline, but it's not, again, really kind of have stylized examples right now. So this would be interesting to understand more broadly. Yeah, I guess I'll just summarize by saying I think this is actually like a pretty interesting opportunity to kind of align theory and practice. Okay, maybe the last thing I'll just say, this is, I guess, kind of a shameless plug for some recent work, but this is perhaps like part of some broader direction I've been thinking about a lot in like the last, year on kind of connections between reinforcement learning theory and like language modeling. I think many problems in language modeling, especially at the post-training phase, are like very naturally modeled as like RL or sequential decision-making problems. Somehow there's much more structured than a lot of the settings that RL theory has been trying to capture over the last few years. Like if you think about language modeling in this kind of token level next MDP, this is actually kind of like a contextual bandit problem where it's like you know the dynamics of the MDP. They're deterministic. So treating this as a reinforcement learning problem, it's actually almost like a computational thing rather than a statistical thing in some sense. But so yeah, this is a place where I so far have been finding it seems like there's actually, I think, a lot of room to have some kind of like interesting interplay between theory and practice where these like algorithms that we derive in theory can actually inform, you know, interesting practical techniques. So this is something that I'm like quite excited about right now. Maybe I'll leave it there. So yeah, thanks a lot.
Yeah,
Oh yeah.
gotcha. So, maybe I just forgot, did you introduce the definition of the recovery parameter? Does it related to the exploration?
It's not really related to exploration. I'll show. Let me show you the definition again. So it's just if we define q pi star as the q function, this is just looking at like the max over all states and actions of the difference of q pi star evaluated at pi star, and the difference and q pi star evaluated at some alternative action. So like the way you should think of this, what you should think of this as saying is like, say I'm in state X, say I take action A, some action A at step at this state, which is not necessarily the expert's action, and then I switch back to the expert immediately after this. What is the most that I pay by doing that? Yeah. So it's just kind of asking like, what is the most that you can pay if you deviate from the expert, but then like switch back immediately?
Okay.
Yeah.
Okay, then I'm a bit confused about
Sure.
the lower bound, like
Yeah.
why, like, I just don't know, like, because I feel like, as you mentioned, exploration can be important factor, like, separate between offline and offline.
Oh yeah, I guess my point is it's separating for reasons that are like unrelated to recoverability.
Oh, okay.
Yeah, that I guess that's the point. It's like,
Yeah, so I just don't know, like, in the lower bound usual,
yeah.
what is the role of exploration, like?
Oh, there's not a role of exploration for that particular lower bound.
Okay.
So I don't think exploration can help in like on every problem instance, and it won't help on the instance that I showed for that lower bound.
Okay.
But what I think what it can definitely help on is like on a per instance basis.
Okay.
So this is the kind of flavor for this result is it's closer to results in like active learning that say like, okay, so you know all the results I've been presenting today, you know, they scale with like 1 over n. So this is like, you know, 1 over epsilon episodes to learn like an epsilon optimal policy. I think what you can probably get for exploration is things that say like, you know, if you have a nicely behaved MDP into expert, then you can get like, let's say like log 1 over epsilon instead of at 1 over epsilon sample complexity. This is kind of in the vein of like classic like active learning results for supervised learning. Yeah.
And another question.
Yeah.
So since you just mainly talk about this kind of configuration inequalities, will the results directly be extended to agnostic setting?
Oh, the agnostic setting? Oh, it's a very good question. I've been thinking about this a bunch. Not necessarily. So it kind of comes back to this unboundedness of the log loss. The unboundedness can be a real problem if you're in the agnostic setting.
Okay.
It's possible to fix this, but as is, it doesn't work in the it will not work in the agnostic setting in general, at least not in like the tightest sense. Like you can prove guarantees for log loss behavior cloning in the agnostic setting. Okay, but you can do better in the agnostic setting with different algorithms. Like, I guess what I'm saying is like sort of the notion of misspecification that you would need to pay if you just use the log loss behavior cloning as is a rather stringent one. Just to give an example of where this can fail. suppose you have two actions, 0 and 1. And you have two experts in your class. One always plays 0 and one always plays 1. Okay, and imagine the true expert plays action 1 with probability epsilon and action 0 with probability 1 minus epsilon. If I draw like 1 over epsilon samples, I will have both 0 and 1 in my data set with like reasonable probability. Okay, and in that case, the log loss for both like the all zeros policy and the all 1 policy will just be like infinity. So you have no way of distinguishing which one is good if you just minimize the log loss.
Is it because you consider maximum likelihood, but here is like both likelihood is 0, so.
Yeah, exactly. So like to handle the misspecified case properly, you kind of need to like smooth things out. Like say smooth the log loss out, or like there are other techniques you can use as well. The interesting thing, this is like something that I guess we'll hopefully write up soon, but like the interesting thing is there's actually non-trivial like computational statistical trade-offs here, where it's like there are ways to fix the log loss that kind of make it perform optimally with respect to misspecification in the agnostic case. It turns out that there are policy classes where optimizing the classic log loss can be done in like poly time, and optimizing this new smooth log loss cannot be done in poly time. But that's actually fundamental in the sense that there's like some real like comp stat trade-off where you cannot attain like the optimal performance under misspecification information theoretically with like any efficient algorithm. Yeah. Yeah, basically, I guess this was like the obvious thing to look at after we kind of like did this work. And yeah, it actually turns out to be a much richer and like not obvious thing than perhaps I would have thought originally, in the sense that they're actually pretty interesting trade-offs.
Thank you.
Yeah.
Any other questions? Any questions online? Yeah. I think we're good.
Okay.
Thank you
Cool.
again for
Thanks a lot.
coming.